I'm going to go through this example problem covering fugacity in the liquid phase. The problem statement says we have a binary mixture of species A and B at 300 K and 1 bar. The vapor pressure of A is 300 K and 80 kilopascals. We're given a plot of the activity coefficient of species A versus the mole fraction, and based on this plot we need to answer a few questions. Part A wants us to specify the reference state for species A and explain. Looking at the plot that they gave us, we can find that the reference state is going to be the Lewis-Randall reference state. This is because for all values of XA, the natural log of the activity coefficient of A is positive. So if you took the exponent of all the Y values on the plot, you'd get that the activity coefficient of A is going to be greater than 1 for all values of XA. And this only happens in the Lewis-Randall reference state. If it was the Henry's reference state, then all of the values for the activity coefficient would be less than or equal to 1. Another reason we know this is because for the Lewis-Randall reference state, the natural log of the activity coefficient of species A goes to 0 as the mole fraction of A goes to 1, since all the interactions are A to A interactions. Part B asks us to find the value of Fa, the liquid fugacity of species A. To do this, I'm going to use equation 7.84 in the text, which gives an expression for the liquid fugacity of a species. At the conditions given in the problem, this expression can be simplified. The fugacity coefficient at saturation can be assumed to be 1 because the vapor pressure that we're given is just 80 kilopascals, which is less than 1 bar, so we can safely assume that the fugacity coefficient at saturation is going to go to 1. This exponential term right here, which is called the Poynting correction, is also going to be equal to 1 because our system pressure is so low. This term is negligible at pressures of less than 100 bar, so at a pressure of 1 bar we can safely assume that this is going to be equal to 1. Since we reduce those two terms to 1, all that's left is that the fugacity of species A in the liquid phase is just the saturation pressure, which is 80 kilopascals. So our final answer for part B is 80 kilopascals. Part C asks us what is the value of HA. I'm going to solve this using equation 7.75 in the text, which says that the activity coefficient of species A at infinite dilution is equal to HA over FA. From the plot that they gave us, we can find the activity coefficient of A at infinite dilution. So at infinite dilution, XA is going to be 0. So at the plot, we go to XA equals 0 and move up and find that the natural log of the activity coefficient is 2.5. So activity coefficient at infinite dilution is going to be the exponential of 2.5. And we can plug that into the equation and solve for HA. When we plug that in, we get that HA is equal to 975 kilopascals. Part D says as best as you can come up with the Margules parameter A in the two-sufफ़ix Margules equation. So to do this, we're not actually going to use this equation because we don't know what GE is, but instead we're going to use an equation from table 7.2 in the book. From the first row and second column of the table, we get this equation, which is what we're going to use to solve for A. We can calculate this at infinite dilution of A since we already used that condition in part C. So again, from the plot, the natural log of the activity coefficient when XA is 0 is 2.5. So we can plug 2.5 in for ln of gamma A, and XB is going to be 1. When we plug all those numbers in, we get that A is just equal to 6,235.5 joules per mole. Part E says, consider a liquid mixture of 2 moles of A and 3 moles of B at 300 K and 1 bar. At equilibrium, what is the mole fraction of A in the vapor phase, Ya? For 2 moles of A and 3 moles of B, you can find that these are the mole fractions. So I'm going to go to the plot and find the activity coefficient at XA equals 0.4. So at XA equals 0.4, the natural log of activity coefficient looks to be about 0.88. Around 0.88. So I'm going to take the exponent of 0.88 to get an approximation for the activity coefficient. This mixture is at vapor-liquid equilibrium, and at equilibrium, the fugacity of species A in the liquid phase is going to be equal to the fugacity of species A in the vapor phase. Plugging in the expressions for the liquid and vapor fugacities of A in the mixture, we get the following. Since we're at a pressure of 1 bar, it's safe to assume that the vapor is going to behave ideally and that the fugacity coefficient of the vapor phase is going to be 1. Once you rearrange the equation to be equal to YA, we have all the numbers that we need, so we just plug in and solve. Our final answer is that the mole fraction of A in the vapor phase is 0.77. Now for part F. F says for the mixture above, determine the activity coefficient of B based on the Lewis-Randall reference state. So now we're going to use the same conditions as in part E, except solving for the activity coefficient of B. From the same table used before, table 7.2, if you look in the third column, you can find this equation, which relates the mole fraction of A to the activity coefficient of B. And we already have all the values that we need. We know A, we know XA, we know R and T, so we can just solve for the activity coefficient of B. Plugging those in, we get a final answer of 1.49. I hope you learned something from this video and that it helped you understand how to solve the problem. If you liked this video, give it a thumbs up and subscribe, and we'll be posting more videos weekly for homework help in Chemie 211 at Purdue University.